Okay, welcome back, students. We are going to go over section 4.3 now, and on subspaces. Let's share screen. Okay, section 4.3. Move on subspaces. Okay, definition. Okay, let S be a non-empty subset of a vector space V. Okay, if S itself is a vector space under the same operations of addition and scalar multiplication, as used in V, we say that S is a subspace of V. Okay. And just note that V has already been established as a vector space. Okay. I know that's kind of like in the first line, but just point out, like, we already know that V is already a vector space. It's already been established as a vector space. Okay, so we already have V as a vector space, and we're taking S from V. Okay. And so S is a subset of V. And so it is a subspace if it still satisfies all 10 conditions that a normal vector space would. So I mean, the main thing here is that, is it closed, and does it have a zero vector? Okay. Is there a scalar 1 that I can multiply by? Because if you don't have 1 in your subset, and if you don't have the 0 and the 0 vector in your subset, then basically you're not going to have a vector space, and it's not going to be a subspace. Okay, but this is saying if we have all of that, and S is a vector space as well, then we call it a subspace of V. Okay, so theorem. Okay, let S be a non-empty subset of a vector space V, then S is a subspace okay, then S is a subspace of V if and only if S is closed under the operations of addition and scalar multiplication. In B. Okay, so we need to make sure that this is that it's closed. Okay, that we don't end up adding something, adding two vectors and getting something outside of S. Okay, that would be bad. Okay, or we end up multiplying by a scalar and getting something outside of S. Okay, we need to make sure that if we start with two items in S, then we stay in S. Okay, we can't go outside of this the subset. Otherwise, it's not closed, and it's not a vector space of in and of itself. Okay, so what happens in S stays in S. Okay, so it's like what happens in Vegas stays in Vegas. Well, if it's a subset, if it's a subspace, what happens in S stays in S. Okay. So number one, let S denote all real solutions of the following linear system of equations. Okay, let S denote all real solutions of the following linear system of equations. Period. Verify that S is a subspace of R3. Okay. I have the following linear system of equations. I have x1 minus 4x2 plus 6x3 equals 0. And negative 3x1 plus 10x2 minus 10x3 is equal to 0. Okay. Notice I have two equations and three unknowns. So my answers are not going to be unique solutions. You only get unique solutions if you have the same number of equations and the same number of unknowns. Then you could possibly get a unique solution. You're not guaranteed, but you could possibly get one. Okay. Okay, so let's create an augmented matrix out of these two equations. And I would get 1, negative 4, 6, 0, and a negative 3, 10, negative 10, and 0. And what I'd like to do is get this in RREF, okay, reduced row echelon form. So let's turn this into RREF. Okay, so the first thing I know is that I have a negative 3 I'd like to get rid of. Okay, so I'm going to multiply the top by 3. Okay, so 3, negative 12, 18, and 0. Okay, and I'll be left with 1, negative 4, 6, 0, and 0, negative 2, 8, and 0. That's 6, 8, and 0. Okay, So that was A1, 2, let's see, 1, 2, 3. Yeah, yeah. Okay, A1, 2, 3. Okay, let's go to the next one. Okay, I'd like to get a 0 here, if I can, for the -4. I'm going to multiply by -2 on the bottom equation and then add that to the top equation, replacing the top equation. Okay, so if I multiply through by -2, I'll get 0, 4. -2 is -16 and then 0. Okay, and so this is going to be A 2, 1 and multiplied by -2. Okay, and when we add that, we'll get 1, 0. There's a 0 that I wanted. Okay, -10, 0, and 0, -2, 8, and 0. Okay, so reduced row echelon form is ones along the diagonal. Okay, so I'd like to get ones along the diagonal here, and zeros everywhere else where there are leading ones. Okay, so since this only has 2 equations, I can only get ones and zeros in the first 2 columns. So I'm gonna just multiply that second row by -1/2. And I end up with, oops, it's a little big. I end up with 1, 0, -10, 0, and 0, 1, -4, 0. Okay, so now I have it in aria form. Okay, reduced row echelon form. And I want to rewrite this, the system of equations with respect to my reduced row echelon form. Okay, because logically they're equivalent from what I started with and what I ended up with. Okay, so I'll have x1 plus 0x2 minus 10x3 is equal to 0. Okay, and then I have 0x1 plus 1x2 minus 4x3 is equal to 0. Okay. So what I'd like to do is I'd like to get everything in terms of one variable t. Okay, and the easiest thing to do is that since both equations have an x3, like a real x3 that I can solve for, that don't have a 0 as a coefficient, because 0 times anything could just be, anything. It could 0 times anything is 0, and the anything could just be anything. It doesn't really give me a good definition for to work with. So what I'm going to do is I'm going to say, look, since x3, -10 times x3 is going to be equal to, add that to x1 will be 0. Then I can get x1 in terms of x3, and I could get x2 in the second equation in terms of x3. So what I'm going to do here is I'm going to let x3 equal t. Okay, and so what does that give me? If I look over here, I can say x1 is equal to 10 times x3, but x3, I just toss this guy to the other side. But x3, we're letting be t, because we can now then write x1 in terms of t. x1 is now 10t. Okay, we can do the same thing with the second equation and say that, look, x2 is equal to 4 times x3, and so x2 is equal to 4t. Okay, and so this will allow me to define, okay, a solution, okay, x1, x2, x3, okay, in terms of t, this variable t, this parameter t. And so x1 was 10t, okay, x2 was 4t, and x3 is t. So I know that, yeah, there's an infinite number of solutions here, yet they have a condition that the first value has to be 10 times the last value, and the second value has to be 4 times the last value. Okay, and so they're proportional. Okay, so there's a proportion to the values. I just can't throw any 3 values in there and say, oh yeah, that was a solution. Okay, there are specific solutions here, just like there's specific solutions to the equation of a line. There's specific solutions to the equation of this plane. Okay, so this is like a family of planes. Okay, well, it would be a plane. Sorry, not a family of planes. Okay, and this would, and the t would just be different 3-dimensional points on that plane. Okay, so we can rewrite this guy as a subspace. So it will be subspace S is equal to all the vector variable solutions. Okay, my n tuple, or my three tuple variable vector, okay, x, which is an element of R3. Okay, so my variable vector, x1, x2, x3, element of R3, okay, such that, little colon there, for such that x vector is equal to 10t, 4t, and t, given that t is an element of R. Okay, so that's kind of that mathematical statement there. It says, look, vector x is a solution to this system of equations if vector x is an element of R3, where vector x is equal to 10t, 4t, and t, given that t is an element of the real numbers. Okay. Okay, so is this a subspace though? You know, this is a subset, certainly, or a set of values, but is it a subspace of R3? And so we already know that, you know, that, you know, R3 is in itself a vector space, okay? All 3-dimensional vectors produce a subspace. So we just want to know, well, do these specifically have a subspace? Okay, is the zero vector contained here? When I add these together and multiply, do they stay closed? So let's just check addition first. Okay, and then we will check multiplication. So all you have to do is check addition, multiplication, and say, yeah, that still holds. Okay. And then we know it's a subspace. If those hold, then and it came out of a vector space, then we know that it's going to be a subspace. It means that it's going to be itself a vector space. Okay, so let's check addition. Okay, so X is equal to 10R, 4R, and R. Let X equal that. Let Y equal, okay, 10S, 4S, and S. And so I'm just saying, look, X we're going to let have the variable R, and Y we're going to let have the variable S. Okay. And so now we're going to add these together. We could say that X plus Y is equal to 10R plus 10S, a 4R plus 4S, and R plus S. Okay. Okay, so that's good. Let's factor out the 10, 4, and a 1. Okay, so we'll get 10 times R plus S, 4 times R plus S, and R plus S. Okay, and we could say that this is equal to 10t, 4t, and t, where t is equal to R plus S. Okay, and so we stayed within the vector, we stayed within the subset of the vector space. And so since we stayed within the subset of the vector space with addition, then one of our conditions is met. Okay, we didn't go outside. If we start with 10, 4, and 1, we end up with something with 10, 4, and 1. Okay, so we say that this does work, this checks. Okay, and so it's closed under addition. Okay. Okay, let's check multiplication. Check scalar multiplication. Okay. So if I take x in this case, and we're gonna do the same thing where we let the variable be equal to R. Gosh, I can't. Okay, so we've got 10R, 4R, and R. And then we want to do K times X. That's going to be K times 10R, 4R, and R. Okay, that's going to be equal to 10 times KR. Okay, and then 4 times KR, and then KR. Okay, and I can group this in such a way, since K and R are just elements of the real numbers, I can group it maybe in such a way that makes it a little easier to see that, yeah, we get something that has the same properties as the original, because again, we're just going to let KR be equal to T. Okay, and so this would be equal to 10T for T and T. And so we start with R's and we end up with T's. And it just shows that, yes, it is closed under scalar multiplication. Again, we end up with something still on the same plane. Okay. Okay. Even if we multiply. Okay, therefore, okay, S is a subspace of R3. Okay. Okay. Let's look at the following one. Okay, number 2. Okay, 2. We want to know if S, okay, is equal to X, an element of R2, such that X equals, okay, that'd be a vector X. I think that's a vector X. Yeah, that's a vector X. Okay. Okay, vector X, an element of R2, such that vector X is equal to T and negative 3T plus 1. Okay, so where T is an element of R. Okay, is this, okay, is S a subspace of R2? Okay, is S a subspace of R2? Are we going to get something that has the same properties that we add or when we multiply? Do scalar multiplication. Okay. So let's check addition. Okay, and so let's check addition. And the addition operation under R2 is just, regular vector addition. Okay. And so let's check addition. Okay. Under vector addition in R2. Okay. Let's do that. And so I'm going to take X again to be R negative 3R plus 1, and Y to be equal to S negative 3S plus 1. I'm going to add these together. Okay, X plus Y. That's going to be equal to R times negative 3R plus 1 plus S negative 3S plus 1. Okay. That's going to be equal to R plus S, and then negative 3R plus 1 plus negative 3S plus 1. Okay, that's going to be equal to R plus S, and then negative 3R plus negative 3S plus 1 plus 1. And so this is equal to R plus S, and a negative 3 times R plus S plus 2. And so if I were to let R plus S equal T, I would get T negative 3T plus 2. And I'm not getting, okay, I'm not getting a 1 there. Okay, and so so it's not closed. It doesn't have the same property as what we started with. So this is not closed under addition. So therefore, it is not a subspace of R2. Okay. So we can see that when we add, it fails. Okay. But not only does this fail to be a subspace, because it's closed under addition, the original S here Okay, the original, the S here fails to be a vector space. And we could have initially seen, hey, this isn't good. That this fails to be a vector space because S does not contain the zero vector. If I let T be 0, I get 0, 1. If I let T be negative 1/3, I get negative 1/3, 0. There's no way, there is no value of T that will give me 0, 0. And so I'll note that S does not contain the 0 vector, okay, to begin with, okay? Now, if your subspace contains a 0 vector, does that mean that it's a subspace? No. It just means that it could possibly be a vector space. We still have to check closed under addition and closed under multiplication. However, the converse is true. If it doesn't contain a 0 vector, then there's no way it's going to be a vector space. Okay. So it's kind of like you could kind of bypass everything, say, was it a subspace? Well, is it even a vector? It could it even possibly be a vector space? Right? And we call that the 0 vector check. So let's finish writing this out. S does not contain the 0 vector. The 0 vector of R2 being 0, 0 is not an element of S. So since any vector space must possess a 0 vector, and S does not, it fails to be a vector space itself. Okay? We know that R2 is a vector space, but because there is no 0 vector in the subspace, or in the subset, I should say, not only is it not a subspace, but it could never be a vector space. Okay, so that's the 0 vector check. Okay, the 0 vector check is if a subset S of a vector space V fails to contain the 0 vector, okay, then it cannot form a subspace. Then it cannot form a subspace. Okay, it has to contain the 0 vector. Okay, so in order for S to be a subspace, it has to contain the 0 vector. So if this is the 0 vector, okay, then S has to contain the 0 vector. Otherwise, there's no way it's going to be a subspace because it can't be a vector space. It's already dead in the water. Okay, let's look at another example here. Example 3, let V equal M2 by 3 of R. Okay, so this is a 2 by 3, all the 2 by 3 matrices. And let S denote all the elements in V for which the entries in each column sum to 0. Okay. Is S a subspace of V? Okay. First thing I'm gonna do is let's check. Let's see if the 0 vector is a part of the subset. Okay. Okay, so is 0, let's 0 vector check this. 0 vector check. Okay, and so we have the 0 vector is equal to, in 2 by 3s, so that's 2 rows, 3 columns, 1, 2, 3, 1, 2, 3. That's the 0 vector. Okay, and does it work that if I add the rows together, add the rows together, that the columns will all sum 0. 0, 0, 0, and yes, it checks. Okay, it still has the same property. Okay, the subset, the 0 vector is a part of the subset. So yeah, it works. So it works. Okay, so what do? We move on to addition and multiplication. Okay, so let's move on to addition and multiplication. Okay, closure. Let's move on to that. Okay, let's check addition. Check addition. Okay, so I want to generalize 2 of these matrices. So I'm going to call matrix A, B, C. Now, if I let the first row be A, B, C, what should I have the second row be in order so that the columns add to 0? Oh, I should let it be negative A, negative B, and negative C. And for matrix B, I should have it be D, E, F, and then negative D, negative E, negative F. Okay. So now I want to add these matrices together, A plus B. And so we're just going to add, okay, element to element, okay, entry to entry. So A plus D, B plus E, and C plus F. Negative A minus D, negative B minus E, and negative C minus F, or plus negative F, I guess you could say. Okay, maybe I'll do that. Okay. Plus negative D, I don't want to skip steps, plus negative E, and plus negative F. Okay. And I'm sure you can see where this is going already, but let's just make sure that we do our due diligence. And I'm going to factor out a negative from each entry on the bottom. I'm going to go A plus D, B plus E, and C plus F, negative A plus D, negative B plus E and negative C plus F. And so if I were to add those rows, they would still sum, or sorry, yeah, add the rows. The columns would still sum to 0, 0, 0, 0. And so it's closed under addition. Okay. So A plus B is an element of S. Okay. What about K times A? Okay, well, so let's check that. Check scalar multiplication. Okay, so if I take K times A, is this still closed? K times negative, or A, B, C, negative A, negative B, negative C. That's going to be equal to KA, KB, KC, negative KA, negative KB, negative KC. And so if I add these, sum these rows together, I still get zeros. So that checks. So KA is an element of S. And so closed under multiplication. Okay, and so since it's closed under multiplication, it's closed under addition. We already know that the zero vector is a part of it. Okay, that's not necessarily that you have to check the zero vector. It's just it's a good first try, because then we could get rid of a lot of stuff. But we could, check a lot of stuff real quickly that would not even be a vector space. It doesn't even have that quality of being a vector space. Could ever be a vector space. Could never be a vector space if the zero vector isn't a part of it. Okay, but the zero vector was a part of it. It's closed under multiplication. It's closed under addition. And so, yes, it is a subspace. Okay, therefore, okay, S is a subspace of V. Okay, let's look at a theorem here. Okay, let A be an m by n matrix period. Okay, the solution set of the homogeneous system of linear equations. So homogeneous, it's a new term. So it's not really a new term. We talked about homogeneous when we were talking about differential equations. Okay, and it's fairly similar, but we just want to talk about it with respect to these matrices. What does homogeneous mean? And that's when I set my system equal to zeros. Okay. And so we let A be an m by n matrix, the solution set of the homogeneous system of linear equations okay, AX equals the zero vector is a subspace of Rn or Cn if complex. Okay, it can be either Rn or Cn. And since Cn contains Rn, If it's CN, then it's definitely RN as well. If complex. Okay, it doesn't have to be complex, but it works with either real numbers or complex numbers. Okay, so we're just saying, look, we're setting our system equation equal to a row of zeros. Okay, and if our system of equations is equal to all zeros, then we call this thing homogeneous. Okay. Okay. So definition. And if it's homogeneous, then it's a subspace. Okay, if it's a homogeneous linear system of equations, then we automatically get vector space identity for this thing. Okay, now that doesn't necessarily play off for other systems of equations, but if my system of equations is equal to zeros, then I'm automatically guaranteed that this thing is a subspace of the real number system or the complex number system. So I don't have to check. Okay, you say, hey, oh, look, the system's equal to all zeros. Boom, we're good. It's a subspace. Okay, that's what that theorem means. Okay, definition. Okay, the solution set, or let's go, let A be an M by N matrix Okay, the solution set of the corresponding homogeneous linear system AX equals 0 is called, so the solution set, okay, of this homogeneous system. So if I get a solution set for this homogeneous system, then this solution set is called the null space. Okay, it's a subset of Rn. It's a subspace of Rn, and that special solution set that creates that subspace is called a null space. Okay. Not only is it a subspace, it's a special subspace that is called a null space. Okay. It is called a null space and is denoted, or of A, null space of A, and is denoted as null space of A. Okay, thus, okay, the null space of A is equal to X, an element of R, such that okay, X, an element of R, such that A X is equal to the 0 vector. Okay. Well, let me see, make sure that that's not Rn. I think that should be Rn. Okay, depending upon which R we are talking about. Oh, it should actually be CN. So yeah, I was right. So CN. Okay. So yeah, perfect. Okay. Okay, and that's the general definition. Okay, and since Rn contains Cn, you could put Rn as well if you were dealing with just the real number system. So let me box this. Okay. Okay. Example 4. Let A be equal to 1, negative 1, 1, 2, 3, 1. Okay, and we want to find the null space of A. Okay, find the null space of A. So we're given an n by n matrix. In this case, it's a 2 by 3 matrix, and we want to find the null space of A. That is, we want to find what happens when we let A times the variable matrix in R3 in this case, because I've got 3 columns, okay, and set that equal to the 0, 0 vector. Okay, so let's look at what this means. We're going to have A, okay, 1, negative 1, 1, 2, 3, and 1, times our variable matrix, okay, and that is, must be, okay, x1, x2, x3, and that's going to be equal to our 0 vector. Okay, so does this work? Let's see what happens. So one, oh, this should be 2. I'm sorry. That should just be 2. Yeah, that's our 0 vector. Okay, because we just have two rows. So yes, that's the 0 vector. Now, does this work dimensionally? Well, let's see. We've got a 2 by 3 vector times a 3 by 1 vector is going to be equal to 2 by 1 vector. So yeah, that works. Okay, those match up, and then the outsides are the dimensions of the resultant vector after I multiply. So that works, 2 by 1. Okay, and what would this look like if I multiplied this out? You know, it would be 1x1 minus 1x2 plus 1x3 is equal to 0. 2 times x1 plus 3x2 plus 1x3 is equal to 0. And then I could create an augmented matrix based on that. So 1, negative 1, 1, 0. Okay, 2, 3, 1, and 0. Okay, so there's my augmented matrix. Okay, and I want to turn this into RREF form. Okay, so let's do that. let's multiply row 1 by -2 and add up to row 2. So -2, 2, -2, 0. And we're going to get 1, -1, 1, 0, 0, 5, -1, 0. Okay, the next thing I want to do is get rid of this guy. Okay, so I could multiply the top row by what? I could multiply the top row by 5, but then that would go into the second row, and I don't want that. So what I'm going to do is I'm going to actually multiply the bottom row by 1/5 so that I can get a 1 there, a 1 here. Okay, and then add. So let's add the bottom row to the top row, a 2, 1, and then go 1/5 times that bottom row. And so we get, when I multiply by 1/5, that becomes a 1 and a -1/5. Okay, and so I get 1, 0. 1 plus -1/5 is 4/5. Okay, 0. And then I get 0, 0, and then 5 and -1. Okay, 0, 5, -1, 0. I guess I could have multiplied through by 1/5 first and then added. Either way, doesn't matter. Okay, so let's just get rid of that 5 now. So multiply row 2 by negative or positive 1/5. Okay. And I will end up with 1, 0, 4/5, 0, 0, 1, and -1/5, 0. Okay, so now that's REF. Okay. And so I want to write this reduced row echelon form back as a system of equations, but this will help me solve for my variables. So this gives me x1 plus 0x2 plus 4/5 x3 is equal to 0. And then 0x1 plus 1x2 minus 1/5 x3 is equal to 0. And like before, we're going to let x3 equal t, so we can get all of our variables in terms of t. Okay, so if I take x1, I toss this guy to the other side, I get -4/5 t. And if I replace x3 with t, toss this guy to the other side, I end up with x2 is equal to 1/5 t. So that tells me that my result is -4/5 t, 1/5 t, and t. Okay. And so this is, not only is this a subspace, okay, but it is a null space as well. Okay, of R3. Okay, or C3, whichever you want to say. So the null space of A is equal to the X resultant vector, okay, variable vector, okay, an element of R3, okay, such that x is equal to negative 4/5 t, 1/5 t, and t, given that t is an element of R1. And that's my null space of A. Okay. We can piggyback on this and say that there's a theorem that says the set of all solutions to the homogeneous linear differential equation y double prime plus a1 xy prime plus a2 a2x of y is equal to 0, that homogeneous linear differential equation, okay, that's a second order, okay, linear differential equation, that guy, okay, when I go to try to solve this guy, I end up with solutions, okay, that, and it ends up giving me a system of equations, okay, that are equal to 0, and then I solve those system of equations, okay, but because I end up with a system of equations equal to 0, it's automatically a subspace, and it's automatically a vector space, behaves like a vector space. And so this is a vector space. No period there. Is a vector space. Okay, the solution space, okay, takes the form y of x equals c1 of y1 of x plus c2 y2 of x. Okay, so there's some constant times a function of x plus some constant times a function of x. Okay, and oftentimes those functions of x are exponentials, ends up being like exponentials. Okay, and that is 4.3. Okay, and I'll see you in the next video.